Download this code from codegive.com, link in the description below. Exceptions are evil? A pragmatic look and alternatives with code examples. The assertion that exceptions are evil is a deliberately provocative statement that challenges the conventional wisdom of using exceptions for error handling. It doesn't mean you should never use exceptions, but rather that overuse or misuse of exceptions can lead to subtle bugs, decreased performance, and difficult to maintain code. This tutorial will explore the arguments against overly relying on exceptions, present alternative approaches, and provide practical code examples in Python to illustrate these concepts. Why the controversy? The arguments against excessive exception use. Here's a breakdown of why some developers argue against excessive reliance on exceptions. 1. Exceptions break the control flow. The fundamental idea of structured programming is to create predictable, linear code flow. When exceptions are thrown, this flow is disrupted. The execution jumps unexpectedly to a try, except block, potentially skipping code that was intended to run. This can make it harder to reason about the program's behavior and to debug. 2. Performance overhead. Throwing and catching exceptions can be relatively expensive operations. Even if an exception handler simply logs the error and continues, the process of unwinding the stack to find the appropriate handler, then executing the handler, consumes resources. If exceptions are used frequently for expected conditions, not truly exceptional errors, this performance cost can become significant. 3. Obscured program logic. When exceptions are used to handle common, expected scenarios, the primary logic of your code becomes entangled with error handling code. This can make the core functionality harder to read, understand, and maintain. The reader has to mentally keep track of multiple potential execution paths. 4. Error propagation can be opaque. While designed for robust error handling, exceptions can sometimes make it harder to track down the origin of a problem. A deeply nested function might raise an exception that propagates up through multiple layers of the call stack, eventually being caught in a high-level handler. The original context of the error can be lost in the process. 5. Testing challenges. Code that relies heavily on exceptions often requires more complex testing. You need to ensure that every possible exception is caught and handled correctly. This leads to a larger number of test cases, including negative tests for error scenarios. 6. Encourages lazy programming. It can be tempting to simply wrap large sections of code in try, except blocks without properly considering the potential errors that might occur. This can mask underlying problems and lead to code that's brittle and difficult to debug. It becomes a crutch, rather than a carefully considered approach. 7. Tight coupling. In some languages like Java, the checked exception system forces you to declare which exceptions a method might throw. This creates tight coupling between the method's implementation and its callers. If the method's internal implementation changes and it starts throwing a different exception, all callers must be updated to handle the new exception. This can make refactoring code difficult. Python doesn't have checked exceptions. When are exceptions appropriate? Before we dive into alternatives, let's be clear, exceptions are valuable in certain situations. They're well suited for truly exceptional errors. When something unexpected and unrecoverable occurs that prevents the program from continuing normally, example running out of memory, a network connection failing unexpectedly, a corrupted file. Critical failures. Errors that indicate a serious problem with the program's state or data integrity. External system failures. When interacting with external resources, databases, APIs, file systems, exceptions are often the best way to handle connection errors, resource unavailability, or invalid responses. The alternatives, returning error values and the result pattern. The core principle of the alternative approaches is to make error handling an explicit part of your function's return value, rather than relying on implicit exceptions. This makes the error conditions more visible in the code and allows you to handle them in a more controlled and predictable manner. 1. Returning error values, error codes. The simplest approach is to return a specific value to indicate an error. This is common in C, and while less common in Python, it can still be a useful technique. Usage. Pros asterisk. Asterisk simple to understand and implement. Asterisk no performance overhead from exception handling. Asterisk makes error conditions very explicit. Cons asterisk. Asterisk can lead to repetitive code if you need to check the error condition after every function call. Asterisk can be difficult to handle multiple error conditions. Asterisk the special value used to indicate an error, example none-1, might be a valid result in some cases, leading to ambiguity. 2. The result pattern, explicit success/failure indication. A more robust and expressive approach is to use a result type, often a class or data structure, that explicitly indicates whether the operation was successful or not, and if successful, contains the result value, if unsuccessful, contains an error message or error code. This pattern promotes a fail fast and make invalid states unrepresentable mindset. Example divide function using the result pattern. Usage. Pros asterisk. Asterisk makes error handling very explicit and forces you to consider the possibility of failure. Asterisk can handle multiple error conditions gracefully. Asterisk promotes a more functional programming style. Asterisk prevents accidental ignoring of errors. The caller must check the result type. Asterisk eliminates the need for special error values, example none-1. Cons asterisk. Asterisk requires a bit more boilerplate code to define the result type and its variants. Asterisk can still lead to repetitive code if error handling is not abstracted properly. Asterisk can be unfamiliar to developers who are used to exception-based error handling. Combining with option types, handling missing values. The result pattern can be further combined with the option type, also known as maybe type in functional programming, to handle cases where a value might be absent. In Python, this can be simulated with optional t from the typing module, but a dedicated option type can provide more structure. In this example, the get_value_from_dict function returns a success result containing none if the key is not found, indicating that the value is absent. This is a more explicit and safer way to handle missing values than simply returning none directly, as it forces the caller to acknowledge the possibility of the value being absent. Error handling strategies with the result pattern. Once you've adopted the result pattern, you can use various strategies for handling errors. Asterisk fail fast asterisk immediately return a failure result when an error is detected. This prevents the program from continuing in an invalid state. Asterisk aggregate errors asterisk collect multiple errors into a list or other data structure and return a single failure result containing all the errors. This is useful when you want to validate multiple inputs or perform multiple operations and report all errors at once. Asterisk retry asterisk if an operation fails due to a transient error, example a temporary network outage, you can retry the operation after a delay. The result pattern makes it easy to implement retry logic. Asterisk transform errors asterisk convert one type of error into another type that's more appropriate for the calling context. For example, you might convert a low-level file I/O error into a more user-friendly error message. Code example, a more complete example with a database interaction. Let's illustrate the result pattern with a more realistic example of interacting with a database, simulated for simplicity. Key takeaways from the database example: Asterisk explicit error propagation. Functions explicitly return failure results when they encounter errors, and calling functions propagate these failures up the call stack. This makes it clear where the errors are originating. Reusing results. The update_user method reuses the get_user method and propagates any failure from get_user, demonstrating how result types promote composition. Validation. The create_user function performs validation to ensure that the input data is valid before creating a user. This helps to prevent errors later on. Clear separation. The code cleanly separates the business logic of the user service from the data access logic of the database. Comparison to exception-based error handling. Let's compare the result pattern to a similar example using exceptions. Comparison table. Feature result pattern exceptions. Error handling. Explicit, part of the function signature. Implicit, relies on try, except blocks. Control flow. Linear, predictable. Can disrupt the normal control flow. Performance. Lower overhead in most cases. Can have performance overhead, especially for frequent errors. Readability. Can be more readable when error handling is complex. Can be less readable when many exceptions need to be handled. Discoverability. Forces explicit error handling, less prone to ignoring. Easier to accidentally ignore or forget to handle. Testability. Requires testing for success and failure cases. Requires testing for different exception types. Boilerplate. More initial boilerplate for defining result type. Less boilerplate initially, but can become more complex. When to choose which approach. Choose exceptions when handling truly exceptional, unrecoverable errors. Interacting with libraries or frameworks that heavily rely on exceptions. Errors are rare and performance is not critical. Choose the result pattern when handling expected error conditions that are part of the normal program flow. Performance is critical. You want to make error handling explicit and prevent accidental ignoring of errors. Building robust and resilient systems. Functional programming is preferred. Conclusion. The statement exceptions are evil is, of course, an oversimplification. Exceptions are a powerful tool, but they can be misused. The result pattern, and variations like returning error codes, provides an alternative approach that can lead to more robust, maintainable, and performant code, especially when dealing with expected error conditions. By carefully considering the trade-offs between exceptions and alternative error handling techniques, you can make informed decisions that best suit the needs of your project. Don't blindly use exceptions, consider whether they're truly the best tool for the job.